Okay, before the break, we were looking at a number of things. Now we need to start talking about something that is, it's critically important for database work, but when we practice this with classroom examples, it's going to seem unnecessary because, well, obviously we're under very tight time constraints in the classroom. So our examples for the homework and even the final project have to be small enough to fit in those time constraints. So it tends to throw people off because they're like, oh, could have just looked at the situation and done that. And in the classroom, yes. But in bigger situations, where it becomes a lot more important, it's not just a look and automatically see the answer. In a real world situation after graduation, working as a data analyst, and you're managing a database that has 5 million records spread across 2,000 tables and thousands of users trying to access that database simultaneously, is very different than a classroom example where we have like 4 tables that we're looking at. So kind of an important thing, but it's easy. It's in a classroom setting, it's hard to see the importance. But it's a set of rules that will guarantee we have a really, really nice database. Database normalization. Let's pull out the notes so I don't go off on a page somewhere. So normalization is the process of organizing our tables, process of organizing tables and relationships to protect data increase search flexibility. So that's what we need for it. Protect data, increase search flexibility. And then there's more to this definition. By eliminating unnecessary redundancy and inconsistent dependencies. Okay, so that definition is a mouthful. Everybody see that on the screen? Neither one of my black markers is super dark. I think the other one kind of quit working altogether. But normalization is the process of organizing tables and relationships to protect data and increase search flexibility by eliminating unnecessary redundancy and inconsistent dependencies. So a whole bunch of big words. So got some clarification to do on that, obviously. Well, I guess clarification, we could put it in one word. We want to optimize it. We want our data to be secure. We want to be able to search reliably and as quickly as possible. And normalization is how we do that. Does anybody have linear algebra? Probably not. Okay, I'm guessing not. I was going to try back into the word why we use normalization. If anybody had seen that in math class, but I'm guessing y'all probably haven't had that in math class. Protect data and increase search flexibility That's the most important part. That's what we want to do. So let me put that in another, in an English statement. So I'll put this with like a little star or something. I guess that's showing up. It doesn't look very dark on the screen. So a couple of commands that we're going to run a lot with SQL that we haven't quite got to yet. Cascade update. And cascade delete. Are not guaranteed to work without normalization. Are not guaranteed to work if less than third normal form. I guess I have to spell it out because I haven't talked about that. Third normal form. There's a nice acronym we'll use for that, and you'll see a lot. It would be 3NF, but that's on the next page of my notes. So we'll get to that in a moment. But that's what's meant by protect our data and increase search flexibility. So these two SQL commands, cascade update and cascade delete, we don't have a guarantee. We can't guarantee that those will work if we're not in at least third normal form. Cascade means changes carry through relationships and will affect multiple tables simultaneously. Otherwise, every field would need changed individually. So when we were previewing normalization the other day and kind of introducing bridge tables to get rid of any many-to-many relationships, I guess that was last Thursday. Our student name might show up in a couple places, or student ID, student email. I think we used email as a unique identifier. Which means that email is also going to show up when it's the foreign key in another table, which is written in a lot of places. Maybe somebody changes their email. Right? They previously had a Gmail account that they set up when they were a teenager, and the username they picked was quite hilarious to them and all their friends. But a few years later, that person wants to have more of a professional representation. Right? They don't want to use that joke name on their Gmail account for their email. So that needs updated. We can go to any of the tables and update it. It's the primary key in the students table that we were looking at the other day. So obviously we have to update it there. But since it's the primary key there, then it's the foreign key over in the courses table or the enrolled course table or whatever we called it. The one every place that showed up as a foreign key, we have to go change it there as well. Cascade update would carry through so that if we changed it in any single one of those tables, it would carry through the relationships and change everywhere. That's the most important thing we get from normalization. Right? That primary key is going to show up in lots of places. If it gets changed and we use something more beneficial than a number, again, just throwing an integer there is a nice fallback if we don't have something. But think about real world situations, not the small classroom examples. If we have 500 million records, that's small for the modern world. But if we threw an extra integer in there, we automatically have 500 million integers in our database that we didn't necessarily need. That's a lot of wasted, that's a lot of extra space used in the hard drive. But they would still get changed, right? Or delete. Maybe we do use the integer primary key IDs because it's nice and easy, and a human's never going to look at that integer. So It doesn't cause us any problems. It gets us all that stuff. But if we delete a record, we have to go through every single table where there's relationships and delete the stuff over there as well. Student table example again, if we deleted the person that had ID number 3, we need to go look through every other table where the student ID was a foreign key and find that 3 so we can delete it there. So cascade delete will automatically carry it through, so that if we delete that record in one row, it will delete or if we delete it from one table, it will cascade through to all the other tables and delete the related records in those other tables. It's kind of an important thing, and as databases grow larger, it becomes more and more important. The difference between 6 tables, the difference between doing that manually in 6 tables versus doing that manually in 12 tables would be more than twice the work. It doesn't necessarily grow linear. If we double the size of if we double the number of tables, we get more than double, basically. So we want this stuff to work. That's why we're going to look at normalization. It also helps to more accurately map real world items and concepts to our database entities. We can put them together in lots of different ways. As long as the data is in storage, it's technically going to work. But in general, we still want it to work in a way that a human can make sense of and dig through and find that data. So the closer it is to the real world representation is better for the humans. The structure or relationships of tables match the way most humans think about it. A great example of that is address. We did this in our table the other day and nobody questioned it whatsoever. Usually, we'll have, it's probably one of the first columns you think of. Go put some sort of person in a database, you're going to think first name, last name, address. But address is usually included in the people table or students table or whatever is representing people in our database. We put address there right with the people, but a person and that person's home are 2 entirely different things. They're not connected, right? Some people move all the time. Some people don't have a home, but they still exist. But because of the way most people think about it, address is one of the first things we're going to throw in that table when we start talking. So having it there is it more accurately models how humans think about the real world object that we are storing data about. Some big benefits of it. The biggest one's here, and it also has some optimizations. This one throws people off in introduction classes because when we get our database normalized really, really nicely, the higher normalization levels, we're only going to go up to the 3rd level. But even by the 3rd level, when we look at it in the ERD diagram, it's going to look like we have more. But when it's in storage, we actually have less. It optimizes the storage space needed. So that throws people off at the introduction level a lot because, well, we're working mostly with the ERD diagrams in this course. A couple people I've already talked to that kind of like the code. They've written a lot of software and prefer and can visualize that stuff their own way instead of using the diagrams. But in general, a lot of people like pictures. Like that old saying, the picture's worth 1,000 words. So we're working mostly with pictures. And when we go normalize our database, the picture actually looks like we added to it. But in reality, when we go create that database, we took away from what it would have been had it not been normalized to store the same data. So that's why we're doing this in the definition. You will definitely be asked questions about the definition. So everybody got that? The screenshot of it. It's okay if I erase the board. I'll wait like a couple seconds. And this one just saves us a ton of work. Okay, I'm gonna go ahead and erase this and we'll start talking about this. And I'm gonna try a different marker, so hopefully it'll show up a little bit dark. Oh wait, actually, I color coded my notes. I'll color code the stuff on the board the same way. And we did see all of this in preview on Thursday. The stuff we were doing, I knew what the next step was. So technically it wasn't in third normal form. There was another clarification point we could have made to last Thursday's example. They used composite keys, but we haven't talked about composite keys yet. Instead of a unique, that ID, that unique field, we put several fields together to make a unique attribute. But we're gonna talk about that when we get to the third normal form. So not having talked about that last Thursday prevented our example from getting to third normal form, but we've seen the steps. It's just talking about the terms that go with those steps. So first normal form is 1 in F. And again, it doesn't seem like it when we apply these concepts in a classroom-sized example, but in the long run, this is one of the most important things from this class. It's probably the most important thing from this class. It just doesn't seem like it when we do it in classroom-sized examples, when we do it with databases that fit in our time constraints. So first normal form, there are 2 rules we need to follow. So the first one is table must not contain composite attributes. Table must not contain composite attributes. And our second rule is table must not contain any repeating groups of attributes. Must not contain any repeating groups of attributes. Which that was actually 2 rules. That's the way it's been written down for decades. For many, many decades, that rule has been written down this way. I think I come across it in a book or something, but the first time I heard it in a class would have been when I was in 8th grade. So long before any of y'all were born. I had an interesting computer education in computers, because growing up in the 80s and in the 1980s and 1990s, there wasn't a lot of people that knew that. So when I was in 8th grade, they built a new middle school, and they put a computer lab in. It was the first time they built a computer lab had been intended on the blueprints. So they had this nice fancy computer lab, but this was 1992. This was the 1991-92 school year. So there weren't a lot of teachers that could teach anything in that computer lab. One person that did know it though, or that did know a little bit about computers, and he taught most of the classes, or maybe about half. He taught about half the classes on my way to school, was the guy that normally taught the agriculture classes and ran the FFA club there at the high school. Because when he was in college, he'd taken some classes on databases, Oracle databases. That would have been the mid 1980s when he went to college. So he knew databases. And his roommate had wanted to be an animator for Disney, and he was one of the first. This guy's roommate in college ended up being one of the first digital animators for Disney. So it was interesting. So he would periodically work on projects with his roommate. So he knew how to do animations and databases. So in most of my computer classes, up until the high school built a computer lab, which was my senior year, it was mostly from that guy, and we studied computer animations and databases because he was the only teacher there that knew how to teach anything about computers. For those who've had me in class before, there was another lesson early. I guess I was in 5th grade. They wanted to make summer school interesting because societal changes and kids couldn't stay home anymore. And that happened like flipping a light switch in 1988. So kids couldn't stay home anymore, and there weren't daycares or any place to send them, so they kept school open and would keep it interesting. And our music teacher's husband was a programmer. So he came in and showed a bunch of us how to write programs on old Apple II machines. That's when I first learned to program, or the first formal class in it. But that time period led to a very interesting computer education. It was very scattered around, just depending on what adults were around that knew something about computers. So the first time I saw this was already here. It was always written as one rule, but it's really 2 rules. Let me break those down. So that's a mouthful. Table must not contain composite attributes. What does that mean? That means one item per column. And the second one, table must not contain any groups of attributes. To put that in normal English, let's say each row must be unique. And notice that I stopped the sentence there. Each row must be unique. And not say that there has to be a unique field. There is no requirement for like that ID field we keep going in. Doing that is just an easy fallback, so we don't have to think very hard about it. Because there's other ways, right? If we had a bunch of people's names and a bunch of people's addresses, well, what we've seen so far, we'd probably throw in that integer primary key. Why do I keep dropping that? We throw in that integer primary key and have a unique field, but that's not really necessary, because if we use those names and their addresses combined, we probably have something unique, right? Up until we got to like juniors and seniors, where kids have the same name as their parents, because they would have the same name and address. Up to that point, we could combine those 2 things and have something unique. So it's not necessarily that one column has to be unique. We just have to have something to make it unique. And doing that with an ID is doing that in one column is a nice, easy way to do it without thinking about very hard about it. But it's the one column isn't required. And that also means no repeating columns. So groups of attributes go both ways. Let's look at something on a spreadsheet real quick. So really that's 2 rules. We don't repeat horizontally or vertically. That's quite the wrong way. We don't repeat horizontally, right? Stretching out, adding more columns, we don't have any repetition And we don't repeat vertically, so as we add more records to our table, we don't have repetition. So we need both of those. I'll just jump over to the spreadsheet real quick. So the students table is a good example again. A good trivial example for a classroom. Part of that being that student records were one of the first things to make it into relational databases. So for about half the people in the world, our entire educational pathway, our records were already in a computer database, a relational database. So we got used to seeing at least what our own records look like because of how the school organized our data. But maybe we'll have a students table. And let's see, we have a name. And the student's going to register for a course. So let's say Jimmy example registers for a physics course. The students register for more than one course. So let's make a course 1 column, a course 2 column, a course 3 column. So Jimmy example registers for physics and I don't know, some computer science course. I'll do an STEP course. I'll do this course, DBMS 110. So he registers for a couple of courses. Then Sally something registers for an English course and the database course and I don't know, maybe a course in Python. So we have a couple different courses, with maybe a third person. Mark made up registers for the database course. So again, the DBMS 110 and maybe a math course and Python course. I started to put the SQL course in there specifically. I was going to make the announcement at the end of the day today. I did register this. I did schedule the SQL course to run in the fall. If anybody's wanting to take the SQL specific course, the one that is just like a big programming course. But I'm going to talk about that at the end of the day or at the beginning of the day on Thursday. So we have these examples, but it's definitely not first normal form. We need to make some adjustments. So we need one column, one data field, data point per field. So our name, we probably want to split that up into first name and last name, which a lot of people are used to doing anyway, right? I guess we could still have our course 1, 2, and 3 there. If I copy this down, paste that in there, and then just bring these examples down. So Jimmy example and Sally something and Mark made up. Another student registers at the last minute. So we need to add somebody to our database. So maybe Nathan, not real. Sounds like a good name. He comes in all excited about core classes, so he's going to take that database class, just like others. IBYT, maybe he's a new student. So that's what we call them here, the Welcome to College courses. He's going to take that course, and maybe then he's going to take the Python course, and then an English course, and then take the database course. But we hit a problem. We don't have enough columns to add a 4th course here. That's our second rule for the first normal form. No repeating groups of attributes. There's another problem here as well. There's not much organization. Ran out of room. So we would need to split that up further and organize our courses so that we had a way to add more if somebody wants to take a fourth course. Or, yeah, that's basically the idea. We need something to happen here. Make that bright red. There's a problem with that. Ran out of room. Because those repeating courses, we have to add a column. I have a bunch of problems here. So there's already at least one empty cell. That empty cell is going to cause us problems. If we add another column, we're adding a whole bunch of empty cells. So that would cause us a problem. But when we went to search for this, some of these people have the database class as their second one. But for this person that's listed as course one, and on that one we ran out of room for, it needs to be a course 4, but that would be a complete overhaul of this database structure. So repeating things, we want to be careful. That's really first normal form, is repeating things. So no composite attributes. So that's one field, one data point per field. Split up your name. That's usually the argument for splitting up an address. And then we do the number, the street name, the city, state, and the zip code all separate. But the argument for not doing that is that those are a single entity. Anytime we search for stuff, we're almost always going to search for the whole address. Maybe split off the city number or state so we can filter it down by city or state. But the number and street name always go together. We don't separate those. So there's different ways to approach it. The argument for splitting it up is first normalization, which basically comes down to no repeating. Don't repeat things. Don't repeat things inside a column. And don't repeat things horizontally or vertically. And we do that. Once all that's assured, then you'll be in first normal form, which helps a little bit with the improvement. That's the first step on those improvements. What else did I have? I have a couple more notes I want to add on first normal form. I guess I'm going to run out of room, so I'll put them over here in green. I have my notes color coded, so I figured I'd go with these. But these markers do seem to be working better than that black one anyway. So values in the same column must represent the same thing. About different records, I'll add that in there. The different records is kind of trivial if we follow the actual rule written in blue here. I'll go ahead and throw it in the sentence. This is one of the things I do that's really, really sloppy on databases, especially ones for software. Or if I'm going to if the database is actually going to hold computer code, like the database is going to hold a bunch of compiled C++ code that's in machine language and a human will never even look at it. I've made databases that every column is a block before, and just put whatever in there as long as it's in the table, and then it's more like a spreadsheet. And the software that goes with that database will work fine because it knows exactly where everything's at in that database. But it's an awful mess, and it's definitely not something that can be updated easily, and not for human reading, not for humans to look at. It's for machines to look at only. In general, this is how most people would describe the database, but I did that on purpose on this example to hint at the problems. So like if we tried to query this data set here, some of the students have DBMS 110 as the course number 2, and some of them have it as course number 1. So that would cause problems. So even with the multiple courses there, which violates our rule, we shouldn't split those up. If data is stored as course number 2 for one student, it should be course number 2 for every student. Otherwise, things become too disorganized to work with. And first normal form completely prevents that. The next point I put here, this is what we get out of it. So no changes to table structure are needed to add a record. This one went wrong with that example I made up. Well, I made it up specifically to go wrong. It was one of the things that went wrong there. When we went to add that last student in, well, that student wanted to take 4 courses, but we only made columns for 3 courses. But following the rules for first normal form will assure that these things don't happen. And I used up the whole board, so I need to erase that to talk about second normal form. It's okay if I erase that? Do I get that in notes or take a picture of it? You will be asked these things on tests and quizzes repeatedly, not just in this course. Normalization is going to be one of the most important takeaways from this course, which I'm explicitly stating that because it's really hard to see when we go through when we practice normalization with an example that fits in a classroom. But in the long run, especially for those heading on to that analytics work, that will be the most important takeaway from this course. The next one is second normal form. And from the first acronym, you probably already guessed how we abbreviate that. So 2NF for second normal form. Actually, our first rule here isn't much of a rule. The first rule is database must be in first normal form. So we can't even get to the second part. We can't even get to the rule for second normal form if we don't do 1NF first. Hence the numbered on them. And then the actual new part here, a relation must not contain any partial dependencies. Must not contain any partial dependencies. There's a term I have to define here, but I'm going to do the normal English version of that rule first. So to put that in something, it's like normally, closer to normal English, let's say each non-key field, and we do still have more to talk about with keys. I mentioned composite keys, those are in today's lecture notes, but uh, there's also other layers of keys because the key is something unique. But what about the difference between, is it unique for the entire database? Or is it unique for the thing we're doing right now? Because sometimes unique for the thing we're currently doing will be enough. So we'll talk about, there's still a lot more to talk about on keys. But each non-key field must be about the same thing. As the primary key. So the table contains data about only one type of thing. One and only one type of thing. That example from just a few moments ago has a great version of it. So this part of the table, we could add an ID here, right? 1, 2, 3, 4. We have that in. So this part of the name table is definitely about our student. We have an ID number, their first name, their last name. But what about this field? Is this field right here, if I make that green, is that field really something about this student? Not at all, right? I did make up this example specifically to fail. So hopefully everybody looked at that when I was typing that up and immediately knew courses should be off in their own table somewhere. But that gets us into second normal form. So hopefully when I was typing that up, if you thought those courses need to be somewhere else, they need to be in their own table. First and second normal form come very natural to people. Third one takes a little bit of work, but after you've made a few databases, you'll probably make most of your tables in third normal form right off the bat. But that's our second normal form. We have stuff in this table that is not the things in our table are about a different real world entity. So I need to define a word here, partial dependencies. So if I share my screen, the way this is set up, the course 2 column depends on the student name column. And the student name, so not on the primary key. Well, I guess we could argue it back to the primary key, but it's only partially dependent on this because this version of the course and the next row down depends on a different primary key. So they're not fully dependent on it. They're partially dependent, or the full term for that is functional dependency. Two different, oops, that's not how to spell different. Two different or unique things depend on the same field.
I'm putting a note here. So what's going to happen most often with that? Most often, that's going to be one primary key instead of two.
So like the example that I just typed up a moment ago for things going wrong. The courses depend on the student primary key, the student ID number, which should be the students uniquely depend on that. But the courses, depending on which students are taking that course, would depend on the primary key in different manner, would depend on different primary keys. So really those courses should have their own primary key somewhere. Things depend on one primary key when it should depend on several. I'll change that too to several because obviously we could, if our database grows large, we could depend on a lot more than just, we could combine more than what should be two tables. Could combine things that should be 4 or 5 different tables. Every non-key field only depends on primary key is a better way to remember functional dependency. Every non-key field depends only on the primary key. Almost what I wrote here. Our rule for second normal form is just a slight extension on functional dependencies, but said in a different way, taking the opposite. So instead of the functional dependencies, the ones we want, we're looking at partial dependencies. And then when we turn that rule into normal English, all our non-key fields just have to be about the same thing as the primary key. Whereas a functional dependency, the non-key fields depend on the primary key. Subtle differences, but when data sets grow large, those subtle differences scale up like everything else. It doesn't scale up linearly. If we double the size of our database, there is more than twice as much work to do. So subtle differences like between this sentence and this sentence scale up just like everything else. So as we get to more interesting examples, they have a bigger impact. But again, I took up the whole board again. Is it okay if I erase this? Nobody's saying don't erase yet, so I'm gonna go ahead and erase this. Functional dependency is a very important technical term that you will see on lots of multiple choice quizzes. So our weekly quizzes in here, as well as midterm and final, but also not just in the classroom. Remember to get certified, get certifications that show you're an expert in databases, such as CompTIA just created a new one last year. So there's a very low number of people that can get in it. I've been trying to push it through the school as quickly as possible. Make sure our students are some of the first ones that have that, because it gives an advantage. But CompTIA just created a Data Plus certification, which CompTIA has the big name certifications for all of IT. So if you're among the first ones to get that Data Plus certification, it will be very, very beneficial for job searching. But for certification, to get certifications, you don't get certified in databases by sitting down and doing a bunch of database work. You get certified in databases by sitting down and answering a bunch of questions about databases. One more of these to look at. That's going to be third normal form. And just to clarify, that's one more to look at in today's lecture, or really for this class. For this class, we only need to get up to third normal form. Normalization does go on after that. 4, 5, and 6 are pretty important if you are a data analytics student specifically, and you plan on doing data analytics work all the time. You probably want to set all your databases up to 6 in that. But for this class, we just need to go to 3 in that. So the first rule is a trivial rule, just like in 2NF, but as is kind of standard, the trivial case is not a trivial situation. So first off, we have to put our database in 2NF. Database must be in 2NF, second normal form. And the rule we're adding this time is relations have no transitive functional dependencies. No transitive functional dependencies. So our functional dependency has to be a direct functional dependency. We cannot translate through another data field to be functionally dependent on our. Any field we have has in our table has to be functionally dependent on that primary key directly. And we can't say like go through the address column to get a functional dependency back to the primary key. It can't translate through. Transitivity. Some of y'all might be noticing some words that you've heard in math classes. I'm actually getting ready to learn a couple more math terminology, but transitive is another important one in math class. Good work. So let's put that in normal English. I'll use red for the normal English. No other data would need changed if you change a non-key attribute. This is the part where addresses fall apart. As far as that debate that it just kind of comes down to personal style, which generally doesn't make much difference. But if somebody moves and you need to change the street number, you probably have to change the street name as well. Right? If somebody moves to a new address, they might still be in the same city, so city and state are fine. But street name and street number go together. So in order to tie those attributes back to the primary key for that record, they translate through each other. Right? If somebody lives at 222 Market Street, just about every city in America has a market, so not any particular example. That's one of the most common street names. So if somebody lives at 222 Market Street and we go to change that, or if we take either piece separately, if we take 222, does that mean anything? House number isn't something we can do math with. And your house and your house number plus your cousin's house number, if you try to add or subtract those, it doesn't tell you anything about another person in your family. 222 by itself doesn't mean it means lots of things, but it doesn't mean the same thing as 222 Market Street.
that relationship has to translate through the other half. So that is a transitive functional dependency. Those always go together, but since that particular one is kind of debatable. Because sometimes when people move, they just move up the street. It's very common for people who live in apartments that once a year they move to a different apartment. It's kind of like a thorough cleaning. Lots and lots and lots of people do that. They'll just they'll move 5 apartments down into one that is has been emptied and completely cleaned out, but otherwise is exactly the same as the apartment they just moved out of. And they'll just bring all their furniture and pictures for the wall, and they'll set it up in the exact same orientation. And it's still like they live in the same place, they're just a couple doors down, because that one is completely clean. That's a very common thing. So we could change the street number without changing the street name. That happens a lot. Or people that rent houses, maybe they want to stay in the same neighborhood. Where's a good example? Old Louisville, those houses on going out 3rd Street. Right, there's some really, really nice old houses. People really, really like those. And a lot of people want to stay in that neighborhood because those, the houses built between 1880 and 1910. Those houses have a lot of character, way more character than a new house, way more character than a house built in 2020. So we want to stay in that neighborhood, and maybe they're one that's like 2 blocks down from St. James Park or something, but an apartment in a building that's basically next door to St. James Park opens up. A lot of people in that neighborhood would jump quickly to get to that one right next to St. James Park. So there's the street name's not changing, but the street number would be. So they're separate data fields, but at the same time, they translate through each other in order to form a functional dependency to a primary key. What other notes did I put in? What else did I put in my notes? If it seems like a second primary key, it should be. So something that shows up, if it shows up repeatedly doing transitive relations, so continuing that bad example that I have on my screen, maybe we want to include tuition. And this person took 2 classes, so that's going to be, I don't know, what, at some college, let's say $1,000 per class. This person took 3 classes, so that'd be $3,000 per class. $3,000 per class. This one wanted to take 4 classes. We were in our room in our database, but that would be $4,000. At some point, we start to see a dependency there that seems like it should be a primary key. That should be maybe not a primary key, but at least a candidate key that we can use to routinely search things. And yeah, a good rule of thumb is if you ever think that, if you start to think, okay, this should be a key on its own, then you probably need to restructure your database and make that a key on its own. The other note I had here, 2+ fields, so 2 or more fields need changed for updates. Also put the note to go with that. Something depends on something that depends on something else. And this is that address example I was just talking at length about, right? When somebody moves, the city and state are most likely the same because it's a much bigger move to move to a different city. So those are the same, but the street address, the house number and the street name would both need changed. So that's why those are commonly given as a composite field at least. Because they don't necessarily stand on their own. They kind of fall apart when we get to third normal form. That has been a long running debate. So if you just want to separate them, if you want to keep them separated, nobody would argue that it wasn't in third normal form because you had your street number in its own column and the street name in its own column instead of making them a composite value. But that's the best trivial example of it. Those two things go together. That example I just put in the spreadsheet, the cost of tuition for each one of those students, that would actually be a bad one. It's a much lengthier discussion, which we'll talk about on Thursday. It'll fit in Thursday's thing, but you should never store data that you can calculate. So in that case, the tuition was based on how many courses they took. So we could easily count how many courses each student took and then calculate what the tuition was. So we don't need to store that value. Age is probably the best example because a lot of times people want to store age in a database, but age is the current day minus their birthday. So we can very easily calculate that and then just store the birthday. Y'all have probably noticed that over the years. Most things, unless the question is, are you over 18 years of age? Because that's an important one for other parts of our society. Most things ask for your birthday, not your age. So you should not store data that can be calculated. That relates to third normal form. But when we talk about this in example situations, we'll see that. So I have some other terminology here. Composite keys are trivially functionally dependent. If we take two fields to make that unique record or make that unique identifier instead of a single field and make a composite key, then obviously there's a transitive functional dependency there, but it's a trivial case which we use to clean things up and get into third normal form without creating a whole bunch of extra data, like without creating a bunch of extra ID integers. So that one's allowed and generally considered trivial. So for like a little example on this, so first name, actually this is some terminology. I was going to introduce it for example. First name is going to be functionally dependent on person ID. Person ID or whatever ID number we put in there. So in this case, person ID is called the determinant. And first name is called the dependent. And for a lot of people, this is one of the situations that it feels like the arrow points the wrong way. So when we notate that, the determinant, so person ID, and then we point at first name. So when we notate this, the arrow's pointing this way, but for a lot of people, it seems like we read it backwards. So first name depends on person ID. So we point on in the depends on relation. The depends on order. That one tends to throw a lot of people off with that notation, and they'll get it backwards, except that one of them is usually an ID, which makes it obvious which way it goes. But sometimes those arrows, because of how it would be handled purely mathematically, if anybody has had linear algebra or even like previews of linear algebra in some algebra course where you're doing matrices, working with matrix things, probably recognize the words normalize, functionally dependent, determinant, dependent. Those are all straight from linear algebra in the mathematics. And we get into the pure mathematics, this arrow makes sense. But because when we put it in English and use the word depend, like first name depends on person ID, in English it seems like the arrow goes the wrong way. Makes perfect sense if we're talking about like normalizing a matrix and our dependent variable reacting to a change in the determinant as far as pure linear algebra. But y'all probably haven't had that course. The big thing for us, any relation, whether it's across the record, mostly across the record, but we want to be careful about relationships between tables as well. Relations have no transitive functional dependencies. So if you change something, you have to change anything else. When we go to make a change, we want to change one and only one thing. If you're going to make a change and have to change several things in order to get that update in the database, then there are transitive dependencies in there. Those rules get us up to third normal form. We want to get at least that far, because if we don't get to 3 and F, then we can't use cascade update and cascade delete with a guarantee. They might still work depending on the database, but they're not guaranteed until we get up to that point. Which means if we go make an update to our database, we have to go through every single field and change stuff every place in which it shows up. So an important thing, and on Thursday, we're going to look at this in examples and try to change some of those technical terms a little bit more back to English and analogies and visualizations and things to make sense of them. Because ultimately, this is probably the most important thing to take away from this class. But for the examples that fit in our classroom, it's not going to see it. It's not going to seem like it, because we're going to look at examples that we could probably look at, and they would almost end up in third normal form, just knowing the very basic ideas of databases. But we want to do it to specifically practice these rules and commit those to memory. Does anybody have any questions about those? Okay, I assume 5 seconds of silence means there's no questions. If you have any, let me know. I'm always happy to help. Otherwise, I will see you all on Thursday. It's a really nice day outside. I was excited. Finally, the day that I brought a sweater, but I didn't wear it. I figured I should still bring a sweater because it might get cold later. But yeah, finally in short sleeves again. So it's a really nice day outside, and probably a good time to enjoy that nice weather. But otherwise, I will see you all on Thursday. Everybody have a good one.